So now in this lecture we'll be doing Claisen condensation reactions. So first of all, these are condensation reactions of esters. Necessary condition is which have alpha CH atoms. Okay. Criteria is that there should be at least 2 alpha CH atoms for the reaction to occur. Okay. Herein beta ketoesters are formed as products. These can also be called as 1,3-dicarbonyl compound. Now, the base used for the reaction is not hydroxide but OAT, as hydroxide will cause hydrolysis of esters to acids. Okay, let's look at the general scheme of the reaction. So if you have R CO2 and a base something like a sodium ethoxide is used, then the product that we'll be getting, it's better to keep RCH2CO2. Okay, because we need this alpha CH atoms. Alright, so we will be getting RCH2 C double bond O CH2, not CH2 but CHR CO2. So suppose if you are using CH3 CO2, then you try to think of that you have CH3COET and a hydrogen that is there with the alpha carbon next to the ester of other ester. So simply now here what you can do is take out this portion, okay, and that will give you your product, which is CH3 C double bond O CH2 CO2, and this is called ethyl acetoacetic. Acetate. also abbreviated as EAA. Let's go for the mechanism of the reaction. Now suppose you have CH3CO2 ET and you're using NaOET. Here is your base. So this will be abstracting the alpha CH atom, leading to the formation of carbanion, which now gets resonance stabilized in this manner. Now we can think of that this particular carbanion will make a nucleophilic attack on the carbon or carbonyl carbon of another ester, and what we will get is something like this, that is CH3CO minus OET CH2 C double bond OET. Okay, think of a proton exchange reaction or transfer. Then we get, okay, not this, sorry, this will come back and that will go away. So we will be getting something like this. Alright. Now to students it might appear, okay fine, I have the product. Okay, I have the product. But that is not what is happening in the real reaction. Now this is a reversible reaction, so this particular product is now lying in equilibrium. Now to separate or take it out of the equilibrium, we need excess amount of sodium ethoxide, which will now react with another proton or abstract another proton, making an anion, and this now separates out of the reaction medium as a salt, which when hydrolyzed, okay, with mild acid will give you the desired product. Okay, so this is mild acid, okay, not enough to cause hydrolysis of the ester, but enough to protonate this thing. Okay, so now we understand why we need two such protons. The first proton is taken at the initial step when a carbanion is formed, which will make a nucleophilic attack to another, the carbonyl of another ester. Now, once this is formed, to take this molecule out of the equilibrium, to make this reaction irreversible, okay, rather, so we will require excess amount of sodium ethoxide that will make a salt of this ethyl acetoacetate, which can be further acidified to give the product. Okay, now let us take up some examples, okay, for practice. Say suppose you are given something like this. So obviously utilizing two molecules such like that, here is a hydrogen, as I have said, take it out, and you will get your product. Now the easiest way of verifying this is this is your alpha and this is your beta. So this is a beta keto ester. This is a beta keto ester. Let's do another example. Say suppose you are given a similar reagent. So all you need to do, and then you have your phenyl, your hydrogen, and obviously your CO2 ET. Again, you take out okay. So basically your ETOH you take out. So instead of doing the whole mechanism, one can go to the product by using what I'm showing you over here. Okay, so this is your and that is your CO2 ET. Just verify this is alpha and that is beta. So this is again a beta keto ester. Okay, now we will be in taking one of a lecture in which I will be collecting a lot of problems from other uh, books and doing whatever I'm teaching over here as a problem solving section. Okay, so let's not take other examples. We'll just do another thing, which is like say how to get starting materials. Okay, now suppose you have been given so this is basically, as I said, it's a 1,3 dicarbonyl, or you can say beta keto ester, right? So how to know what was the starting material of any beta keto ester? Now remember, all you need to do over here, you start the numbering from the ester 1, 2, and 3. You disconnect in the 2,3 bond. Again, you're making a heterolytic cleavage. Place the positive charge over here and the negative charge over here. Placement of charge is very important. Now to neutralize the negative charge, you add one H plus. So this is basically CH2 becomes CH3 CO2 ET. And over here, you have two choices. Either you can add Cl minus or you can add OET minus. Okay. So if you do that, that means your OET goes in here. You do that, you have a Cl or you have OET. Okay. That is how you can get your starting materials, which means these esters will combine to give this product. As simple as that. Now, for crossed Candizero reaction, very similar to crossed Claisen condensation reaction. Now, if esters, okay, we are condensing two different esters. Okay, if two different esters are condensed, okay, there can be two conditions. A, both have alpha CH atoms, then we will get four possible products. We are using the same analogy as we have used in the case of ideal condensation reaction. Okay. Now, if we are having one has no alpha CH and other has alpha CH, then two products are possible. Okay, we will see how this is happening. So suppose we have taken, I'm discussing the case number B. A we don't need to do. Suppose I have taken molecules such as these which have no alpha CH, something like that. Okay, so these have no alpha CH, so they cannot form carbon ions. All right, and nucleophiles cannot be formed from here. Now if I have taken, suppose, this in combination with this, then it is pretty sure adding NaOET, hydrogen will be taken, H abstraction will happen from here. H abstraction will happen from this molecule, which means from only one molecule I will get the nucleophile. So the choice is what? This nucleophile that is formed from ethyl acetate can go and attack this one, and eventually OET will be replaced, or it can go and attack here and eventually OET will be replaced. So when two same molecules combine, then as we have discussed before, we will be getting the ethyl acetoacetate. But when two different ester molecules combine, now the product here will be something like this. Okay, so we can see now two different products are forming. Okay, all right, next. We will be discussing intramolecular Claisen condensation reaction. Also, this is known as, also called, Dickman condensation reaction. Okay. Now, takes place for molecules that have two ester groups. First thing, your product will be cyclic beta keto ester. Okay, now suppose we have been given this molecule. That is the ethyl ester of a adipic acid. Okay, and this is treated with NaOET. followed by mild acidic workup. So obviously now we can think that OET will take up, this is your alpha CH, so OET will be take up your H from here and a minus will be formed here, so this will attack here and that will go away. So now that means a 5-membered ring will be formed. A 5-membered ring will be formed. We'll do the mechanism in detail, don't worry. And so this is your alpha and this is your beta. So this is your beta beta ester. Let's do the mechanism. How this is happening. So suppose that is your ester group. This is your another ester group. You have used ethoxide. This has a hydrogen. This is taken up because it is a acidic hydrogen. Now this is your OET, CO2ET. Here is your minus. This minus will attack here. sp2 carbon converts to sp3. Sorry. Okay. Now this will come back. That will go away. Eventually forming cyclic beta beta ester. Okay. Let us do some practice problems. Suppose something like this is given to you. Try to find out the alpha CH. So this is your alpha CH. Now in presence of OET, we can think that this hydrogen can be abstracted. Okay, we use a different ink for clarity. This hydrogen can be abstracted. So what can happen? It's better to learn the mechanism for such molecules. Okay, so it has CO2ET. There is your minus. This is your CO2ET. Okay, now try to think here an attack takes place. Okay, so this will open up, meaning what? We have got this is say 1, 2, 3, 4, 5, 6, 7. Okay, so we need to make a 7-membered ring. All right, something like that. So suppose this is your CO2ET. That will be your O minus. That will be your OET. So this comes back. That will go away. That means your product over here will be something like this. Sorry. Again, a beta ketoester. Okay. Let us try another one. Something like this. Again, to do with OET minus. So this is your alpha H. Take this out. Minus is here. OET. Obviously, mechanical flick attack over here. That opens up. Try to make a ring count. 1, 2, 3, 4, 5, 6. So now we can generate a 6-membered ring. First, you generate the ring. Suppose I have said this is the 6th carbon, that means this is O minus and this is OET. Okay. So 6 is joining with 1. So this is your carbon number 1 that is having CO2ET. That is how you have to practice. The third carbon is having methyl group. So this is 1. So this is 2. This is your 3. Now this will come back and that will go away. Eventually your answer will be okay. So always numbering the carbons and then creating a ring helps. Okay. So I think that is a better practice to keep, and chances of things going wrong are very less. Now, as we have seen over here, to how to make compounds like beta ketoester in the Claisen condensation reactions. Now, suppose if you are given a starting material, right? Find products from starting material. So in that case, suppose I have given you something like this. Again, ester carbon is 1, this is 2, this is 3. Disconnect at 2 and 3. This carbon will be bearing the positive charge. This is having the negative charge. Okay. Now where you have placed positive charge, you add plus O minus OET. Addition of minus OET over here like this. And here you add plus H plus. So the answer becomes now something like this. Okay. Don't worry, we will be taking up a sheet of problems, as I said, from good books, and then I will be compiling them, and I will be showing how to use this technique that I'm showing you over here in that another lecture. Okay. So whatever shortcut techniques I've shown you, it will be we will go for another practice of this in the next say another reaction. We are saying the acetoacetic ester synthesis. Okay, so what do we prepare over here? Now, useful method to convert alkyl halides, okay, into methyl ketones. Okay, let's have a look what we're trying to do over here. Say suppose I have given you ethyl acetoacetate. Along with that, I have said treat this with NaOET. Okay, so obviously this active methylene group will be deprotonated, leading to the formation of a product something like that. Okay, now if such a molecule is treated with something say like Rx, which is a alkyl halide, okay, now these alkyl halides can undergo SN2 type reaction, okay, and we can get a R attached over here. Interestingly, if you hydrolyze or carry out acid hydrolysis, then the ester gets hydrolyzed to acid. Now we know beta keto acids on heating, okay, they undergo decarboxylation. I think that is very much something that we know. So just trying to give you the idea what we had done before. So what is to happen is this bond goes in here, that goes for here, and this goes in here once we heat it, okay, on heating. So CO2 is going outside from where? From here, okay. So now what is formed? R C double bond OH. This is a enol, and enols they tautomerize to keto compounds. So this is your methyl ketone part. Okay. So as I have discussed, method is useful for conversion of alkyl halides to methyl ketones. Okay. Now let's do a few more practice problems, just to give you an idea. Okay. Now suppose same thing, ethyl acetoacetate, you treat with NaOET, presence of ETOH, excuse me. So that is what forms, and you have reacted this with say benzyl bromide. Okay, attack will take place here, this will go away. That means OET, now that gets joined to your phenyl, and you do acid hydrolysis. That means beta keto acid will be formed if you heat it. Decarboxylation will take place, which means this portion of the molecule will be gone, and my answer will be something like this. Okay. A interesting part over here I'm telling you. Suppose you have treated this with NaO, NaOET, ETOH, number one, followed by Rx. So you know by this time, this is what you will get. Now, if you treat this with another molecule of NaOET, then obviously this hydrogen will be taken up, right? That means if I use again Rx, another R will be coming in place of a hydrogen. So what I can say is we have now two such R. Okay, we have two such R, which if you treat with acidic water followed by heat, means decarboxylation, again this portion will be gone. So my answer will be what? R. That is my answer. Now, next, what we are studying is called Perkin reaction. These are basically condensation reaction of aromatic aldehyde with acid anhydrides in presence of sodium, potassium, salts of the same acid. Okay, and results in the formation of alpha comma beta unsaturated aromatic acids. Okay, now here again, if you try to achieve the product by a mechanism which is a huge one and a complicated one, it is going to be a painful act. So try to follow what I'm trying to say over here. All you need to do is draw the aldehyde. Okay, this is your structure for acid, and I'm writing it like this so that I can take out water. That is CH3CO, all right, C double bond O, C double bond O, and that is your CH3. So this is basically acetic anhydride. Okay, now all you do is take out water. Okay, and you have been given a NaOOC CH3. Okay, heat around 150 degrees centigrade. So this Now you can think, is forming something like that. All you need to do is carry out hydrolysis now. Now if you're doing hydrolysis, just think, whenever you treat an anhydride, so this is also an anhydride. Okay, an anhydride, when treated with water, two molecules of acids are formed. So what you do is you disconnect here. Here you add H plus, and here you add OH minus. That is what you do. Okay, so your answer will be now. This is called cinnamic acid. Along with that, you will get acetic acid. Important part here is that acid anhydride should have two alpha CH atoms. That is the requirement of reaction. Besides that, no reaction takes place in the absence of the acid anhydride. Okay, let us do some examples, I suppose, which we obviously call practice problems. Alright, so number 1, here I have given you furfural, and we are treating furfural with acetic anhydride in presence of followed by now if you just critically note, this is your benzaldehyde. So to benzaldehyde, technically you're adding this unit, or I can say to any aldehyde I have to add this unit. I repeat, to any aldehyde I will add only this unit in a Perkin reaction. Okay, so that means for this reaction I will add, just keeping the same analogy, this is my CH, which will form a double bond, right? And what do I add? CH, COH, okay? CH, COOH, and that is my answer. Again, number 2. Suppose you have been given cinnamaldehyde, okay? Which is something like this. Same reagent, okay? Again, this is your aldehyde part, okay? So to that, what do you add? CH, COOH, that's it. Number 3, suppose you have been given benzaldehyde, but I am changing the anhydride now. So I've given you CH3CH2CO So this is the anhydride of propionic acid. Okay, so the salt also should be CH3CH2COO minus Na plus acetic workup. That means alpha carbon of the anhydride. So this is the alpha carbon. So which means now, okay, this is your alpha carbon. Okay, that is your answer. Next. Suppose you are given salicylaldehyde. Okay, and this is treated with same reagent. Again, CH, okay, CH followed by COOH, and that is your OH. Now, what is interesting over here is you can write the other geometric isomer. So this is, you try to write the other geometric isomer. Okay, now you have OH and then you have OH in presence of heat. Okay, so these two structures, just I'm changing the orientation, and they cannot say they are equivalent, but try to change in this way. Now try to take out water from here. So the molecule that we get has a name, and this is called Kumari. Okay, so we end our lecture over here today, and the next section we will start is Novenagel reaction.